Hello folks, this lesson is on electromagnetic induction, transformers, and a little bit on motors and generators as well. So a very important relationship does exist between when you have an electric current and a magnetic field. So induce really does just mean create. And what this kind of says is that whenever you have a current, whenever you have electrons that are moving through a conductor, so this is our wire or conductor here, and if we have electrons that are going through from the left to the right, as soon as you have those electrons that are moving, it automatically induces or generates an electric field. So we can determine the actual shape of the magnetic field around the conductor using what is called the right-hand rule. So the right-hand rule simply says that you grab onto the conductor, as it's showing in this picture down below here, with your right hand grabbing onto this conductor. Your thumb points in the direction of the current. So here we can see that the current is going up, and your fingers, they show the direction of the magnetic field. Symbol for magnetic field is capital B. You don't need to do any calculations for the magnetic field, but you should be able to determine the direction of that magnetic field. So your fingers wrapping around, what that means is that on one side of the wire, your fingers are going in one direction, and on the other side, they're going in the opposite direction. In other words, the magnetic field is actually wrapping around the wire. So if I just draw another wire here again, with the electrons going from the left to the right, that means at the top here, if you were to grab onto this wire with your right hand, that means that at the top, it would be coming toward you. That is the magnetic field. And at the bottom, it would be going away from you. So it's wrapping around that conductor. Well, you can also have wire that's not straight, but it can be wrapped around where we have many loops relative to the length. So this picture that it is showing here, it is referred to as a coil, or it's also called a solenoid. So again, that's where you have many loops compared to the overall length of this structure. So this is the basis also behind electromagnets. I'll show you a little bit of an animation here in a second. We can also determine the direction of the magnetic field around a solenoid as well. So again, we're going to use the right-hand rule, only now it's a little bit different. So in this case here, what it's going to tell us is the direction of the magnetic field on the inside of the solenoid. So here you're going to grab onto the solenoid again with your right hand. Now your fingers are going to show the direction of the current. They're going to wrap around the solenoid in the direction of the current, and your thumb is going to be indicating the direction of the magnetic field coming out of the center of the solenoid. Okay, so in this picture here, it's showing us with these arrows the direction of the current going through the solenoid. And we can see that the fingers, they're pointing in the direction of that current. The thumb is the direction of the north pole of the magnetic field, where it comes out of the center of the solenoid. So not on the outside of the solenoid, but coming out of the center. Now remember that for magnetic fields, the direction of the magnetic field is north to south. So if we do have it coming out here, then it's going to loop around the outside of the solenoid and come in through the other end. And of course, this is going to be three-dimensional rather than the two-dimensional piece, paper or screen that we're seeing here. So let me just escape out of this PowerPoint and show you a couple of animations. So this one here that we're taking a look at, all we have is a stationary magnet where we have a south pole and a north pole. Remember, any magnet, it does have to have both the north and the south. It's not like electric charges where you can have positive or negative. With a magnet, you do have to have both. So whenever you have a permanent magnet, there is always a magnetic field that is around the outside of that magnet. And again, it's always going from the north to the south. So this kind of shows us the magnetic field lines that we would find around this magnet as well. It also has a compass here. We can move this compass around, and what we can see is that, yes, as we do go around the outside of this permanent magnet, we're going to have the compass that's changing directions. So this is the north pole of the magnet. So opposites attract, which means this little white portion of the compass, that must be the south pole of the compass. The opposites do attract. Okay, so white is going to be the south pole. If we bring it around to the other side here, again, opposites attract. So red must be the north pole of the compass because this is the south pole of the permanent magnet. So kind of related to a solenoid. So with the coil of wire, what we saw is that if we do have a current that's going through a wire, it can generate a magnetic field. If we do have a moving magnetic field or a fluctuating magnetic field, it can do the opposite. It can induce a current. So a current can create or induce a magnetic field. A fluctuating or moving magnetic field can create a current. And that's what we're going to show here. So in this animation, again, we have our permanent magnet. And now we have a conductor in the form of a solenoid, which is connected to a voltmeter, allowing us to measure the voltage. We can also just switch this to a light bulb. Take a look at the light bulb. The light bulb is not on. So how do we get this light bulb to turn on? Well, we have a permanent magnet. We have a magnetic field. But notice that these little dots here, those are the electrons in the solenoid. They're not moving. So in order to get the light to turn on, we need to get those electrons moving, which means we need a fluctuating magnetic field. Take a look at what happens as soon as I move this magnet. Oh, as soon as I move it, the electrons start to move in the solenoid and the light goes on. So I'm just going to take this magnet and I'm going to move it over to the other side. Notice that the light is not on. I'm going to take this magnet and stick it right inside the center of the solenoid, and notice that the light is not on. I'm going to put it on the outside down below if I can. And again, the light doesn't go on. Well, of course, we did see the light flickering on and off. So when was that happening? When I'm moving the magnet. So stationary magnetic field created by this permanent magnet does not get the electrons moving, but as soon as I have a changing magnetic field, that is what does allow the electrons to move. So let's switch this over to the voltmeter, and let's see what happens when I take the north end of this magnet and stick it into the solenoid. Okay, so as I move it in, take a look at the voltmeter, and then as I pull it out, take a look at what happens. So as I stick it in, we get electrons going in one direction, indicated by the negative voltage. As I pull it out, the electrons go in the opposite direction, indicated by the positive voltage. Okay, north end in, electrons go in one direction, pull it out, electrons go in the opposite direction. Bring the magnet or the magnet over to the other side, south end now, stick it in, the electrons go in one direction, pull it out, the electrons go in the opposite direction. This is really the basis behind a generator that generates what is called alternating current. So with alternating current, the electrons don't start at one end of the conductor and go to the other end. They jiggle back and forth. They move a little bit in one direction, they stop, and then they go in the opposite direction, they stop again, and they just continue to go back and forth. Take a look at what these blue electrons are doing in the conductor as I move the magnet back and forth. Okay, they move in one direction, then they move in the opposite direction. Take a look at the voltmeter. It shows a positive current, then a negative current, just the voltage, indicating the electrons again are going in one direction and then the other direction. How did I do that? Changing the magnetic field. This is the basis behind an electrical generator that generates alternating current. It is alternating current that we use when we plug a device into an electrical outlet. That is alternating current. More or less, this is an electrical generator, a fluctuating magnetic field, having the electrons jiggling back and forth. This is an electrical generator that I'm showing you right here. If we take a look at the light, moving the electrons back and forth, moving the magnet back and forth fast enough, if I could do it fast enough, would keep this light turned on. So again, that's the basis behind electricity, or what we generally consider to be electricity, which is the alternating current. So we'll take a look at a couple of other animations in there in a second, but let's go back to PowerPoint here. Continue on with the next slide. So changing magnetic field inducing current. So that is what we did just see, and that's what it's showing in this picture here as well. So this again is the solenoid that we just saw in the animation. We're inducing or creating a current in the coil by moving the magnet back and forth. And in this case, they have the north pole. So when you take the north pole of the magnet, or sorry, it looks like it's the other way around on this one, where they're taking the south pole of the magnet and sticking it in. The electrons go in one direction. And then if they were to pull this magnet back out, the electrons would go in the opposite direction. And again, that would generate the alternating current. Again, a stable or unchanging magnetic field does not generate current in the wire. You have to be changing that magnetic field in order to generate, induce, or create a current. So this is also the principle behind how transformers work, how motors work, and how generators work as well. I do want to go back to that previous animation just to show you the basic principle behind electromagnets and how electromagnets work. So back to this one here. So here what we have is our solenoid, and here we have electrons that are going through, and this is using a battery which does generate direct current. I can switch this to alternating current, where the electrons jiggle back and forth. But let's start off with the DC, the direct current here. Electrons going through that solenoid. This is our compass. Let's play around with the compass a little bit here. Remember that we use that right-hand rule to determine the direction of the magnetic field in and around a solenoid. So yes, let's use the compass for that. So if I take this compass and bring it really, really close to the solenoid here, remember that as these electrons are going through, it generates a magnetic field, and we can use that right-hand rule to determine the direction of that magnetic field. So here, if we take a look at this compass, we can see the orientation of the north and the south pole. If I move it to the outside of the solenoid, notice that now it flips around. So inside the solenoid, the magnetic field is going in one direction. On the outside, the magnetic field is going in the opposite direction. If I bring it around over here again, so we can see the magnetic field, this is what it would be on the inside. This is what it would be on the outside, if I can drag it down here. And again on the inside of the solenoid. And all of these arrows around the outside are really showing the same thing. And that is going to be that the magnetic field is going through the center of the solenoid in one direction. Around the outside, it's going to be going in the opposite direction. So when you turn this on, what we have now generated is a permanent magnet. If I were to turn this off, we would no longer have a magnetic field. So this is not a permanent magnet. This is a temporary electromagnet. You only get the magnet when it is connected to a power supply. If we switch this to an AC current, we get this sinusoidal wave here. Electrons are jiggling back and forth, and that also means that the magnetic field is flipping from one direction to the other on the inside and the outside of the solenoid. Once again, back to our PowerPoint here. I have another presentation that is entirely on transformers. So just one slide here, and we'll go back and we'll take a look at that animation again. So transformers, first of all, you need to understand that they do not work with batteries. They do not work with direct current. They only work with alternating current. And that's what it's showing in this picture here, where we do have the voltage. This is showing the sinusoidal curve of the voltage that's coming into this transformer. So we'll talk a lot more about this in the lesson just on transformers, but what they do is they change the voltage. So the voltage coming in on the left-hand side is going to change it to a different voltage on the right-hand side. So the P stands for primary, that's the incoming side. Secondary, that is on the other side that we're transforming the voltage and the current into. So it involves two different coils or solenoids around. It could be a soft iron core or a laminated iron core. Current flowing through this side here. This is our current. Generates a magnetic field. So as the current is going through this wire, what we're going to get is a magnetic field, capital B for magnetic field. There's no connection between these two solenoids, but if we generate a magnetic field, not only do we use a current to induce a magnetic field, we can use a magnetic field to induce a current and get electrons going through this other solenoid here. So as we'll see, this can either increase or decrease the voltage and the current on the other side, on the secondary side. So very, very useful device for either what we call stepping up or stepping down the voltage. Again, I'll just escape out of here so we can go back and take a look at a very nice little animation here once again, which is showing the transformer. So here what we do have, and actually let's just go to DC first of all, because it doesn't work with DC. Here we have our DC solenoid. We have electrons that are going through. So with these electrons that are going through, it is going to, as we saw, generate a magnetic field, but it's not a changing magnetic field. So when we bring this other solenoid, this would now be our secondary solenoid. When we bring it in close, nothing happens because we don't have a changing, we have a constant magnetic field, and we need a changing or fluctuating magnetic field. So now, if we switch over to AC, what we'll see is that as the electrons start to jiggle back and forth in the solenoid on the left-hand side, that induces a magnetic field when the electrons are going in one direction, and it flips the magnetic field around to the opposite direction when the electrons go in the other direction. Again, at the top here, this is showing a change in the voltage. It's showing a change in the current as well through the primary solenoid. Magnetic field that's generated will then induce or cause the electrons to jiggle back and forth in the secondary solenoid that we have as well. And again, we'll talk a lot more about transformers in a completely different lesson and do some calculations that go along with that. So finally in here, I wanted to talk a little bit also about motors and generators. There are DC motors and generators, and there are AC motors and generators as well. So first of all, motors. What motors do, and this is very important for you to understand, motors are going to take electrical energy and convert it into mechanical energy. So think about something like a table saw. It's taking electrical energy and it's converting it into the energy of turning that blade in the table saw. Okay, so that is what a motor does do. So it can be a DC or it can be an AC motor. This one here that I'm showing you a picture of, this one here is for a DC motor. So current is going to induce a magnetic field around a conductor, and that's going to result in repulsion close to the permanent magnets that we have in this diagram. So these here are our permanent magnets. This is a motor, so what we do need is a power supply. This is our power supply here. This is our voltage, and in this case, because it is a DC power supply, this is a battery that we're talking about. So as the electrons are going through this conductor here, coming from the battery, they're going to make contact with this metal ring here, this half ring commutator, and that's going to allow electrons to go through this ring-shaped conductor as well. So as the electrons are going through, that's going to generate a magnetic field, and that magnetic field is going to oppose this south pole here. And what that's going to result in is the turning of this coil. On the other side, the magnetic field that's generated on this side is going to oppose, it's going to be north as well, so it will oppose this one and it will repel, and that's why we see the turning in a clockwise direction of this coil of wire that we have here. So this kind of motor, it does have this ring here, which is called a split ring or a half ring that we do have, and this is the indication here that you're looking for to indicate that this one is a DC motor that we have. So we have current that's going through the conductor, it's reaching this split ring and going through this coil of wire where we do have contact between the commutator and this split ring. But notice that there's this little bit of a gap here. So when there is a gap, there's no current that's going through, and it's the torque that's created that's going to continue to move this coil of wire. So that's going to result in the rising up of this here, and that's why this is a motor, because what we have done is we have taken electrical energy from the battery and we've converted it into the turning of this motor. So that's our conversion of our electrical energy into the mechanical energy. Let's just take a look at the other pictures that I have here first of all before we go to the animations. So now for generators, an electrical generator, again, equally important that you know this, they do exactly the opposite. So they convert mechanical energy into electrical energy. Looks like kind of a similar setup here, and this is going to be for AC voltage that is created, alternating current. So what we need to have is something that is turning this crank here. So this could be water in a water turbine, in an electrical generating station using hydroelectric, or it could be in a coal or nuclear electrical generating station where it's steam that's going to be turning this crank here. So as we turn that, we have these permanent magnets on either side, but we have this fluctuating conductor inside of a magnetic field, which is the equivalent to a fluctuating magnetic field. So if we're turning this in this magnetic field, that's what's going to get the electrons going. And because of this design that we have here with two different rings, as we'll see, that's what's going to generate the alternating current. So the rotation of the conductor loop within the magnetic field is going to induce the movement of electrons. And again, it's the two-ring design that we see here, which is going to be indicative of the alternating current. So this one here, it looks kind of similar, only now this one is for direct current. So what to look for in this case is we don't have the double ring, but we again have this split ring that we're taking a look at here. Same thing that we saw for the motor. In fact, the motor and the generator, they're exactly the same setup, only in one case we're using mechanical energy to produce a voltage. In the other case, we're using the voltage to produce mechanical energy. So in this particular case here, we have something that is going to be rotating the crank. When it rotates it around this magnetic field, we're going to generate a voltage, and this is what the voltage here, the voltage graph, is going to look like. So this one here is what it's going to look like if we have a direct current, and this is what it's going to look like, the sinusoidal curve, if we have the alternating current. Let's just go then too and take a look at a couple of these animations from the internet where we can visualize this a little bit better. So let's take a look at the generator on this one here first of all. So this one here is going to be for alternating current. So this would be very similar to hydroelectric, where when we turn on some water or get the water flowing from behind a dam through an electrical turbine, the turbine blades are going to turn, and that's then connected to a solenoid like we have here, or at least the magnetic field is going to have an influence on the electrons in that solenoid. So here we have a permanent magnet, but right now it is generating a magnetic field. If we move this around, we can see that there's a magnetic field, but it's a stationary magnetic field. What we need is a fluctuating magnetic field. We need to get this magnet moving. So how can we get it moving? Well, we allow some water to pass through. So this could be water in a hydroelectric generating station. It could be wind in a wind turbine. It could be steam in a coal or natural gas electrical generating station, or in a nuclear generating station. So now take a look at our compass. The magnetic field is changing. We have a magnetic flux, we have a changing magnetic field, and what this can now do is get the electrons moving in our conductor, which in this case is a solenoid. So we do have the electrons that are jiggling back and forth, which means this is again electric current that we are generating. So if we just open up the flow of water here a little bit more, we get the electrons jiggling back and forth at a faster and faster rate, and we get the light being on, well, almost continuously. Again, take a look at the compass. We're changing or fluxing, altering that magnetic field very, very rapidly, which is leading to the jiggling back and forth, the alternating current in these electrons of a solenoid going back and forth, generating electricity in the form of alternating current. A couple of other ones that I'll show you here as well. So the still picture that we're taking a look at, this is for a DC motor, and let's just read through a little bit of this together here. So a simple DC motor has a coil of wire that can rotate around a magnetic field. So we have our stationary magnets up above and down below. Here we have our coil of wire, and this is our single split ring once again. So it is a motor, so we need a power supply. This is our battery power supply, and the idea is with a motor is we want to turn this. We're taking electrical energy and converting it into mechanical energy. So when this battery is connected, electrons are going to be going through, but they only complete the circuit when we do have this brush in contact with the metal part of the split ring. Where we have the gap, it interrupts the flow of the electrons. So right now we have contact between the brush and the split ring, which means current is going through the conductor. When the current does go through, it generates a magnetic field around that wire. So that magnetic field, if we take a look at the picture on the right hand side here, so we can see that north and south, they are opposites, they will attract, so that will lead to the spinning. But if we allow that attraction to take place, then once this cylinder that it's showing here was vertical, it wouldn't spin anymore. So we have the current flowing and the magnetic field and the spinning taking place when it's in contact with the brush and the split ring, but then you need a gap so it doesn't stop when we do have those opposites that are attracting. So that's the idea behind a little bit of the split. Then torque or momentum will allow it to continue through until it reaches the next connection point. So this one here is showing us what's going to be taking place with our motor. So again, we can tell it's a motor because we do have a power supply. This is the symbol that we do use in a schematic diagram for DC and for a battery. Current is going through, but it's only completing the circuit when we have the brush that's in contact with the metal portion of the split ring. So that allows for the spinning, as the magnetic fields are going to be attracted to each other, going around the wire and with the stationary magnet. And then we want the momentum to continue to rotate it until the brush makes contact with the other half of the split ring. So that's for a motor. At the bottom here is for generators. So they do say here that the DC motor and the generator, they look exactly the same. Only now, instead of having something that is generating the current, we're going to be turning this. We're going to be physically rotating it, and that's going to generate a voltage, and that's going to generate a current. And this is the graph again that we saw before, which is the shape of the voltage that we would see that is generated from a DC generator. And finally, this one here is for an AC generator. So as it says in this animation, now we have two brushes that are in contact, and now we have continuous rings. So it's not the split ring, it's the continuous ring that we have here. It also says the two external terminals are always connected to the same ends of the coil. And this produces this sinusoidal graph that we do see that's characteristic of the alternating current. Again, this is a generator, so the point is to generate voltage. So something would physically be turning this. Some sort of a turbine would be turning it. And then we can see the voltage that is generated. So again, what to look for is when you see these two rings here, two continuous rings, that's going to be AC, and this is an AC generator. When you see the split ring, that is going to be for DC. If you're generating voltage, that is a DC generator. If you're using a battery, then that is going to be a DC motor.